Hey guys, welcome back to my channel. I'm back with another video on differential equations. If you're new to my channel, make sure you click the subscribe button and turn on the bell notifications to stay up to date with all the new videos that I upload. In today's video, we'll be talking about solving ordinary differential equations using the integrating factor. We'll be mainly talking about linear first order differential equations. So without further ado, let's get started. So first, we'll have a quick recap on exact differential equations. So if you don't know what they are, or if you want to watch the full video on exact differential equations, I'll leave it right here and also in the description. You guys can check it out. So to recap what exact differential equations are, let's just get started. So let's say we have a differential equation in the following form. We discussed that if there exists a function f of x comma y such that dou f by dou x is equal to m and dou f by dou y equal to n, then we can say that this differential equation is an exact differential equation. And in fact, the solution of that differential equation is actually nothing but f of x comma y equal to c. Now we further saw that the essential condition which we had from that was that if we have dou m by dou y equal to dou n by dou x, this is a sufficient and a necessary condition for the differential equation which is written here. So let's call this one. This condition is sufficient and necessary for one to be an exact differential equation. So we saw this in the previous video and you guys can check that out if you're not aware. So we'll be picking up from this point today, and today's main focus will be about integrating factors, what they are, and how we can use integrating factors to solve linear first order differential equations. So let's take an example to start with. So let's say we have a differential equation y dx plus x square y minus x dy equal to 0. So let's say this is the differential equation, right? So this is m and this is n. So if I see dou m by dou y, it is equal to 1, and dou n by dou x is actually equal to 2xy minus 1. We can see that they are not equal, and therefore this differential equation is not exact. But if I actually were to divide the entire differential equation by 1 by x square, so if I were to do this whole thing times 1 by x square, in that case what I get is y by x square dx plus y minus 1 by x square dy is equal to 0. Now if I were to do dou m by dou y, what I get is 1 by x square, and if I do dou n by dou x, I actually get, sorry, this is, so I made a small mistake in the equation. So this is the actual equation. So now if I do dou n by dou x, I actually end up with 1 by x square as well. So we can see that by multiplying this differential equation 1 by some factor, which we'll call mu for now, we were able to convert it into an exact differential equation. So in short, any such function mu, which mu of x comma y, which when multiplied to a non-exact differential equation converts it into an exact differential equation, is called an integrating factor. Now there could be infinitely many integrating factors for any differential equation, but if we're able to find even one such integrating factor, then we'll be able to convert it into an exact differential equation and we'll be able to solve it. So the purpose which we have from the perspective of solving a differential equation is to find any one such integrating factor. There could be many, an infinite number. There could be an infinite number of integrating factors again. So once I do convert it into an exact differential equation, we know that f of x comma y equal to c will be the general solution of that differential equation, as we've already studied before. So now obviously the main question which we have is, how do we find this mu? How do we find this? So for that, actually, let's think of it this way. Now I have dou f by dou x is equal to m and dou f by dou y equal to n. And we saw that only if we multiply mu into this differential equation, which means I actually have mu m and mu n, only then is it an exact differential equation, right? So our purpose is actually mu m dx plus mu n dy is equal to 0. This is our actual differential equation, and in such a scenario, if I have dou f dou x times x plus dou f by dou y dy is equal to 0. So this is what we've essentially done. We multiplied mu to a non-exact differential equation, it became exact, and we were able to solve it. So now the thing is, the condition which we had initially, which was dou m by dou y equal to dou n by dou x, this was the sufficient and necessary condition for exactness, right? But actually now this will become and mu n. This will be the sufficient and necessary condition which we have. So if I were to expand that, what I will get is mu times dou m by dou y plus m times dou mu by dou y is equal to mu times dou n by dou x plus n times dou mu by dou x. Now if I were to rearrange this, I would get 1 by mu times n times dou mu by dou x minus m dou mu by dou y equal to dou m by dou y minus dou n by dou x. This is actually the condition which it reduces to. So now this is actually a partial differential equation, which is actually even harder for us to solve, right? But what we want is actually one possible solution of mu. This will give us all the possible, if we were to solve this, we would get the general solution of mu, and that could be an infinite number of solutions. But like I said, we are interested in only one such solution, so one particular solution. So now let's assume that the particular solution mu is simply or purely a function of x. So if mu, maybe I'll use another color for distinction. So let's use maybe green. If mu is a function of only x. So this means dou mu by dou x is actually d mu by dx, and dou mu by dou y is actually equal to 0. So if I were to plug this in above, what I get is 1 by mu of x, because we know mu is purely a function of x now. That's a particular solution. We care about only one particular integrating factor. And we'll have n times, this won't be dou anymore, it will be d mu by dx. The next term will be actually 0 because dou mu by dou y is 0. Now we'll have dou m by dou y minus dou n by dou x. So this means that just rearranging, this is what we get. Now let's just call this some function g of x. Why is that? Because the left hand side is purely a function of x. Therefore, the right hand side also has to be purely a function of x. So let's just call it g of x. So if this is the case, then we have 1 by mu by dou x is equal to g of x. And this gives us that mu is actually equal to e power integral g of x dx. So if I were to highlight it in some color, this is the solution for us to find the integrating factor. So just to summarize, we saw that an integrating factor is actually anything that you multiply, any function that you multiply to a non-exact differential equation to convert it into an exact differential equation. Now there may be infinite such functions of mu which will satisfy. Now we did a little math and we ended up with the partial differential equation, which was this. So now it's hard to solve a partial differential equation, and this partial differential equation will have infinitely many solutions, right? But we are interested in only finding one integrating factor because that will solve our purpose. So now if we assume that that integrating factor is simply a function of x, we could assume that it is also, additionally, we could also assume that it's only a factor of y, in which case we will get mu of y is equal to e power integral h of y dy, where h of y will again be where h of y would actually be, I think, dou m by dou y minus dou n by dou x divided by m, maybe minus m. So this would be h of y. So that either we can find in terms of only y or in terms of only x, because we are interested in a particular integrating factor. So now that we found that out, we know how to find the integrating factor. And now this first equation, m was y, n was dou square y minus x. Now you can plug in these results which we got. If you solve it, you will get mu of x is actually equal to 1 by x square, which was one of the integrating factors which we got. Now that we've understood what an integrating factor is and how to convert a non-exact differential equation into an exact differential equation, we will quickly move to linear differential equations. Why? Because they use the same integrating factor concept. And I would say that linear first order differential equations are the most important kind of differential equations that we have. So what is the form of a linear differential equation? So commonly it is written in the following way. So any equation that can be written in this form is called a linear first order differential equation. So now if I were to just simply rearrange this, right? So if I were to rearrange this, what I would get is q, I'm just going to denote q of x and p of x as simply q and p. You have to note that they are both pure functions of x. Only if we can write it in this form, it's a linear first order differential equation, and that's what we are considering right now. So if I were to write it this way, I would get it as right. So now here you can note that m is equal to q minus py and n is equal to minus 1. You can see that this is not an exact differential equation, right? But if I were able to convert it to an exact differential equation, then that function f which I have, x comma f of x comma y equal to c, would give the general solution. So now let's think of it this way. How do I find the integrating factor for this, right? So the way to do that, like, I'm going to use this assumption that it's purely a function of x, right? So I'm going to do 1 by mu by dou x is equal to dou m by dou y, which is simply minus p, minus dou n by dou x, which is 0, divided by n, which is minus 1. So that's nothing but p. So from here I can see that mu of x is actually e power integral p dx. This is the integrating factor, right? We can see this. So now this means that mu m and mu n, these are exact functions, and the way to solve for exact differential equations, we know that dou f by dou x is equal to m and dou f by dou y equal to n. If we do this, we'll be able to solve for f and we will get the exact differential equation solution. We'll be able to find the function f and we'll be able to solve it. So it's good to note that this is the integrating factor for our linear first order differential equation. Now, another way that I'm going to decompose this first equation is that I'm going to multiply. So if I have any non-exact equation, if I multiply it by the integrating factor, it becomes an exact differential equation. We are aware of that. So let's just write it in that way. Let's multiply it by this mu of x. So what I actually get is e power integral p dx times dou y by dou x plus py into e power integral p dx is equal to q times e power integral p dx. We know that now this is an exact differential equation. So if you notice here, the first term, this is actually nothing but dou by dou x of e power integral p dx into y. If we use the chain rule, we actually get that is equal to q e power integral p dx. So now if we integrate on both sides with respect to x, what do we get? We get e power integral p dx y is equal to integral of q e power integral p dx plus c. Now this means that the integrating factor times y is equal to integral of q times the integrating factor plus c. Right? That is one way to write it. Another way to write it would be simply I multiply both sides of the equation with e power minus integral p dx. So then I get strictly in the following way. Maybe again I'll use another color for proper visibility. I'll actually get y is equal to e power minus integral p dx into integral q e power integral p dx integrated with respect to dx plus c. Now this is the solution of our linear first order differential equation. This is a general solution because I don't know what the value of the constant c is. C belongs to R. And based on the initial condition or some particular final condition, based on if it's an initial value problem or a final value problem, we can find the value of c. So we have seen how if we have a linear first order differential equation which is represented in this form, it's not an exact differential equation. So I can find the integrating factor. Then I multiply the integrating factor to the equation, which makes it an exact differential equation. But actually in our case, we are able to find a very nice chain rule of differentiation. So we're able to directly integrate it and find the general solution for the first order linear differential equations. Now, the reason why I showed you how to find the integrating factor per se is because if you don't remember this formula, the final formula, you can always derive it as you solve it. Or if you're able to convert it to an exact differential equation, we already know how to solve exact differential equations. You would have seen it in the previous lecture, the previous video. where we have dou m by dou y is equal to dou n by dou x, right? So we use those conditions and we try to solve it, and we try to find the condition f, and f is equal to c will give us the general solution. So now that we know this, let's just take an example and solve it. So let's say the question which we have to solve is dou y by dou x plus 1 by x times y is equal to 3x. P is equal to 1 by x and q is equal to 3x. So the integrating factor is actually e power log x, which is equal to x. So we can see that from the above, if I were to do it, I would see that x times y is equal to integral of x into 3x dx plus c. So this means that xy is equal to x cube plus c, or essentially y is equal to x square plus c times x power minus 1. This is the general solution of the differential equation. So I used this particular representation over here. You guys can verify that it's actually correct. So that actually concludes the video on integrating factors, how to find integrating factors, a particular one, how integrating factors are used in solving linear first order differential equations, which are by far the most important kind of first order differential equations. You will be getting it mostly in this form when you're asked to solve differential equations analytically. And we saw and solved an example on how to do that. So thank you very much for watching the video. If you enjoyed the video, please do give a like and subscribe to my channel. If you have any questions, do leave a comment or reach out to me via email. I will try to get in touch with you and help you the best I can. Thank you and see you in the next video.